Welcome back to a new week with Physics 4411 or 9411 for those of you following the PhD variant. I wanted to give you just some quick messages before we get started. So the topic this week, after the introductory overview which we went through last week, is to start building up the essential ingredients of a Variational Monte Carlo calculation of the energy in particular, but also other observables using stochastic methods. So this includes Markov chain Monte Carlo as the basic mathematical algorithm, and it involves stochastic variables, random numbers. And in order to accept moves in a Markov chain, we're going to use a famous algorithm, which is called the Metropolis Algorithm. And this is going to be the basic algorithm we're going to implement in order to select new configurations or new states, or simply just accept a move of a given set of random walkers. Then we also need some basic statistics to revisit that, the basics of Markov chain theories. And we also need to discuss how to actually build up the code. This is these are the topics which we will try to cover in the coming weeks, so that at the end, you're going to have a what we might simply call a kind of professional Monte Carlo code based on the variational method. So today we are going to look at some of these mathematical details, and we are going to build in more and more details as we move on. And I'm going to try to give you a kind of overview of what the course is going to contain and which kind of elements we will need to implement numerically. So when we are setting up the code, there is a skeleton here, which is extremely useful. So there was a former TA for this course here, Morten Ledum, and he developed a very nice skeleton for setting up a C++ program. As we mentioned last week, and I'm going to repeat some of the things which we discussed last week, you should feel free to use other languages than C++. One of the reasons why we introduced C++ is that C++ is actually a widely used programming language in scientific computing, together with a language like Fortran, and the latest versions of Fortran contains also object orientation. C++ is widely used, and you will see that the C++ and C are some of the top languages, both in academia and in industry, when it comes to high-performance computing and computational science problems. You should feel free, however, to use Python if you want to. For Monte Carlo calculations, you're going to see that it's going to be a little bit slower than a C++ implementation, but you have ways to speed up a Python program. Other languages like Julia and Rust are also getting more and more popular. So if you wish to experiment with a new programming language at the same time as you perhaps have a, let's say, a Python program which solves parts of the exercises or the problems we are going to look at, feel free to explore new programming languages as well. So we can give you guidance in Fortran, C++, Rust, and Python. We are less familiar with Julia, but both Øyvind and myself, we have actually also programmed Julia. So we should be able to give you some basic guidelines in programming languages which are not included among the 4 canonical ones, which are Fortran, C++, Python, and Rust. So the notebooks, which is we are going to go through a little bit now, they serve to give you the basic elements in a Monte Carlo calculation. And we are going to start with the simpler problem, which we have in project number 1, which is a system which is trapped in a harmonic oscillator potential. So the harmonic oscillator is an idealization of a trapping potential, but you can actually make these potentials in the lab by setting up electric quadrupole fields, and that give you in 2 and 3 dimensions something which looks like a harmonic oscillator potential. So these types of traps are normally called penning traps or Paul traps. And the inventors of these traps. I mean, you're actually using these to trap. You can trap ions, you can trap electrons. They got the Nobel Prize in Physics in '89. And pending traps and Paul traps are widely used for precision mass measurements of nuclei, for instance, but also in the exciting field of quantum computing. That's one of the technologies which is used to trap ions or electrons or other charged particles, which then can be used as a basis for setting up what's normally called qubits. So there is the background for the theory which we are going to analyze has really tight connections with experiments. And the system we are looking at is a system of bosons. So these are integer spin objects. And the final wave function is symmetric, which makes life a little bit easier also when we are setting up the code. And these kind of systems are systems, those which we are going to simulate, are systems which really mimic a realistic situation. And the final calculation you will be doing is something which you can actually relate pretty closely to experimental observations or lots of previous theoretical calculations. Now, to give you a kind of overview of what we are going to do, the topics which we will develop, basically every mathematical ingredient which enters the setup of a program is something which you can reuse in project number 2. In project number 2, we have a path where you're going to apply neural networks or deep learning methods to the same system. And that variant of project 2 is a variant where you will essentially need all the ingredients which you have used and developed in project number 1. And then you need to add on top of that one the setup of a neural network. So that's one possible path. Another possible path is to extend the calculations in project number 1 to a system of fermions. And the typical system then is a system of so-called quantum dots, which are candidate systems for actually making quantum gates. So people are doing that by trapping electrons in small traps, which look like harmonic oscillators. And then the complication then is that you would have to include a wave function which has a trial function, which has a different symmetry. In this case, it's going to be anti-symmetric. But as we mentioned, and as we discussed last week, there is also the possibility to tailor project number 2 to your own interests. It obviously has to deal with quantum mechanical problems. So the notebook which we are going to look at in more detail after we've gone through some exercises on the whiteboard is a notebook which contains the basic elements for getting you started with thinking of a variational Monte Carlo program and the basic elements which are needed in doing so. Now, one of the things I wanted to remind you of before we move on to the whiteboard and slow down the pace a little bit is something which is called the Variational Theorem. And I'm also going to take the liberty of reminding you of some of the things we defined last week. And then we are going to look at these topics in a little bit more detail. So if we just scroll down here, the basics of a Monte Carlo calculation, if you want to look at the calculations in a nutshell, is to evaluate this multi-dimensional integral which you see here. And this is now going to be the expectation value of the Hamiltonian operator. And what you see here is formally the quantum mechanical definition of it. And we are assuming now that you've seen this kind of definition before. And this leads to the usage of something which is called the Variational Theorem, which plays a very important role because we do not have the exact solution to the problem. And in our case, we are going to replace the exact wave function with a trial wave function. And that's why we have this t here. And this is going to depend on the coordinates r. And as you can see here, this r is a vector which contains the positions of all the particles. And we are going to reserve a label n here throughout this course to indicate the number of particles in the system. And then there are some parameters. And these parameters are normally called variational parameters of the model. And you will see why in just some few moments, because these are linked to something which is called the Variational Theorem. And that theorem simply states that if you have the exact energy of the system, so this could be the fundamental state, depends on the symmetry, but it could also be an excited state of the system, depending again on the symmetry. But the variational principle simply states that the expected value you calculate is equal to or larger than the exact expected value for this specific operator here. Now, since this is a multidimensional integral, the stochastic way of evaluating this integral is the kind of standard way of doing that. And when you reach to systems with dimensionalities larger than, say, 6, or with integrals larger than 6 or higher, then typically Monte Carlo methods or stochastic methods for evaluating an integral, they normally outperform standard methods based on discretization of your integration grid. And these methods will be simply finite difference methods or Gaussian Legendre methods, Gaussian quadratures they're normally called, where you combine different types of orthogonal polynomials. And Monte Carlo methods are normally much more efficient for high dimensional problems. And that's why we are going to develop a code for variational Monte Carlo calculations. The mathematics which is needed is less complicated than the kind of mathematics you would have if you deal with other types of many-particle methods. So essentially what we are going to look at are tricks of the trade for solving this integral. And then this is going to be connected with statistics and the topics like resampling methods in order to get better estimates of errors when you do a statistical calculation. And the other topics which we will need to deal with, since we are going to minimize this problem, so this is the optimization problem, we will need to be able to calculate the derivatives of this quantity here with respect to the variables alpha. So we have a problem which is defined by the positions and eventually other quantum numbers of a given set of particles. And we're going to have a vector here which contains parameters in the theory. So the trial wave function, I just wanted to quickly remind you of the variational principle. So suppose you actually have the exact solutions, and this is the way you prove the variational principle. Suppose these are given, you can then expand any function in terms of these parameters psi of I. And these parameters AI, which you see here, these are just parameters in an expansion in terms of an orthogonal basis, which is a complete basis, normally an infinite basis. And these do not depend on the parameter alpha. So in general, and the wave functions which you have here, these are the exact solutions of the eigenvalue equations. And you can expand this ansatz in terms of the exact solution. And what happens then when you plug this in back into this integral, which you have up here, then when you plug it in, you would then get the coefficients in front of here in terms of the sum. And you would have the same for the denominator. And since these are the exact solution, it means that when H acts on this state here, you get an eigenvalue, E of n. And since the states or the state functions are assumed to be normalized and orthogonal, it means that what you get then is simply the energy times a normalization integral. So this integral here is now assumed to be equal to 1 when n is equal to n. And that's why the double sum disappears and it reduces into a single sum. And these numbers here, unless you have the exact solution. So if now this A of I this expansion which you see here of A of I times C of I. If this is suppose you have the exact solution for the ground state, which would typically correspond to I equal to 0, then this sum would contain only E0, because that would be the solution we're looking after. And then you would single out E0, and you would simply have E0 as the final answer. If not, since we are assuming now that these energies are ordered as an ascending series, so E0 is smaller than E1, which is again smaller than E2, and so on, then the energy which you get when you don't have the exact wave function is given by something which is larger than the exact energy you're looking after for the ground state, if the ground state is the state you're targeting here. So this is just a quick reminder about the variational principle, which you may have seen in previous courses in quantum mechanics, and it's pretty easy to prove that one. So we are going to move on to the whiteboard and remind you of some of the things we did last week, and link this up with the build-up of a program, the elements which we need, and also some of the mathematics which we can derive and get analytical expressions for, and then we can compare the code we are developing with these analytical expressions. And that's extremely useful when we are developing a large program, so that we have several small steps which allow us to make sure that the program we are developing is producing the correct results. And I really strongly recommend you to actually pay attention to these small analytical intermediate steps, because they will allow you to gain a kind of confidence in that what you're doing is actually correct. So let's switch over to the whiteboard. And feel free, guys, feel free to use the chat function, ask questions, or unmute yourself if you want to ask questions here. So let's now go back to the whiteboard. So if we look at the ingredients which we are going to need in order to set up a Monte Carlo program. So let's try to list them here. Ingredients needed. To build a VMC program. I'm just using this acronym here for Variational Monte Carlo. Now, what we defined is the expected value of the energy. So we use this notation with E of H here, and that's something which we can rewrite in terms of the kind of standard physics approximation. So this is going to be a quantity which will depend on a parameter alpha. So sometimes you will see this written in terms of a bar on top of it. So that's also another notation for an expected value. But the kind of notation which you may have seen in many, many physics courses, for those of you who are physicists or quantum chemists, is a notation like the one which you see here. So I may change between the notation which you see here, this one. This is the expected value of an operator H, or this notation here. Now, this quantity is given by an integral, a multidimensional integral, where we have defined this R, and this contains the positions, or alternatively other quantum numbers of the involved particles. And this R is an element in a domain which we haven't specified. And we have a trial wave function, complex conjugate, and this depends on the positions of all the particles and other quantum numbers. So now I'm just assuming that I'm leaving out other quantum numbers. And then the Hamiltonian depends only on the position of the particles. And then we have psi of t, so t stands for the trial wave function. And this quantity is then normalized. And this is the quantity which we normally don't want to deal with, because this in principle represents a huge dimensional object which leads just to constant, and we need to find ways to avoid to calculate it. And in the Monte Carlo machinery, this is actually what is going to take place. So we are going to have now the trial wave function squared. And I hope you're familiar with this kind of notation. Now, the quantity which we need is now we want to translate this one into a statistical expectation value. So we need to define a probability distribution function. So this is this PDF. And in our case, the quantum mechanical probability is going to be given by this probability defined by the trial wave function. So that's why I'm putting a T here. And this is given by if we use the standard quantum mechanical interpretation, this is given by the wave function squared. And in our case, since we don't have the exact wave function, this means that we have to deal with the trial wave function. And this is again given by this psi T of R alpha. So this is the definition of a quantum mechanical probability. And what we did last week was also to define another quantity, which we call the local energy. And this is actually the quantity we are going to evaluate, because then we can rewrite the expression for the expectation value of the Hamiltonian operator. We can rewrite that in terms of a probability times this local energy, which we defined last week. So this E of L. And this is a quantity which now depends on, again, on these variational parameters. So in principle, we should put an arrow on top of it. So in the lectures on the whiteboard, I typically use arrows, but in my lecture notes, the online lecture notes, you will find this as a bold-faced quantity. So if we want to be a little bit more picky, we should actually put arrows on top here, because we have a series of such parameters. So this is my bold-faced quantities here. And this quantity here is defined as 1 over the trial wave function of R multiplied with the Hamiltonian operator, which now acts on the trial wave function. And last week, you started to look at the calculation of this quantity here in terms of the specific trial wave function, which we are going to look at in this course here, in this project number 1. So alpha is a series of variational parameters. So this is a vector now which contains a set of parameters, alpha 1, alpha 2, alpha 3, up to some alpha n here. Now, in our specific case, we are going to look at in the first case, we're going to look at the harmonic oscillator. And when we are developing the program, we are going to look at particles which are trapped in a harmonic oscillator potential, and the particles are not interacting in the beginning. And we are going to do the code development with a non-interacting case, because that's going to give us a system which has analytical solutions. So we know the exact solution. And these are very important properties of the system. So when we now look at the expectation value of the energy, so if we go back a little bit here and look at the quantities which we have here, then this expected value can now be rewritten in terms of this local energy and the probability. So it's pretty easy to see if you now go into this place here, in here, and you place just psi of t and divide by psi of t in here, then you can recover the following expression. So what we're going to get then is that the expectation value of the Hamiltonian operator can now be rewritten in terms of the expected value of this quantity E of L as a function of alpha. And I'm going to use this more shorthand notation here, E of L as a function of alpha. And it's easy to see that this can be rewritten in the way we want to deal with things from a statistical point of view. So we have the domain here, and then we have this trial probability of R of alpha, and this is multiplied with the new operator, which we have defined, this local energy. And this is essentially what we are going to look at here. We're going to evaluate this integral using Monte Carlo methods. Now, the quantity which we need to define when we are setting up things now is to first define. So these are the topics which we need to deal with. So we need to define psi of t. So we need to have a model for that. We need to define the Hamiltonian operator h of R. So that does not depend on the variational parameters. And when we have these quantities, we need to define the local energy and also this quantum mechanical probability, which is based on the trial wave function, which we have chosen. Now, when we have this, then we need to start thinking of how we want to structure the program here. So let's now set up some of the basic elements which we are going to need. This follows very much this link which I showed you to Morten Ledum's skeleton for a C++ program. So how do we build a program? How to build a program which solves the equations for the expected value of, let's say, the energy. Now, when we have this trial wave function, when we find the optimal trial wave function, then we can start thinking of setting up other types of observables, because then we have the optimal trial wave function, and that can be used to calculate other types of expectation values. But the basic thing is that what we have done here is to rewrite the expectation value of the energy Hamiltonian in terms of a probability distribution and a new quantity, which is the local energy. So this is the, how to say, the essential mathematics before we get started. So one thing we can do now when we are setting up the program is to think of splitting it in terms of two parts. So the first part which we could think of is what we might call the system. And here is where you would define the types of wave functions, or it's better called trial functions. So that's an ingredient which we need to specify. And as you will see, we will also need the derivatives of the trial wave functions. You would need to set up the local energy. So you need a function for that. So I'm highlighting these quantities here because these are going to lead to functions which you need to define. So you need also to set up a function for the local energy. You need to set up the Hamiltonian. So you can have different Hamiltonians. So the nice thing if you set up this program in an object-oriented, or you define proper functions, you don't need to do object orientation, but you need to define proper functions. Then it's easy to switch to another type of system. So you can actually reuse the whole machinery in project number 2. So these ingredients here are essential parts of the system specification. You may not need to set up a program or a function for the Hamiltonian, but you could do that in case you want to test different systems. So that means that the local energy simply receives as input the wave function and the Hamiltonian. And these could be objects which you have defined. So you would need to set up these quantities which specify the system. And if this is possible, one of the things you should think of is to define this in terms of analytical expression. So if possible, so we're going to put this one in here, if possible, an analytical expression for EL, the local energy, the trial wave function, psi of t, and their derivatives. This is going to be important because we want to optimize the problem and their derivatives. So if it's possible, this is something which is desired. And the reason for that is that if you calculate derivatives numerically, this is often going to lead to many more CPU cycles, because then you would need to make some step to the left or to the right of the position where you are in order to get an additional quantity for the quantity you want to calculate the derivative of. An alternative to you calculating this analytically is to use something which is called automatic differentiation. And this is something which is extremely useful if you're developing a large code. Automatic differentiation is actually an algorithm which translates, using the chain rule, the derivation operations into specific programs or functions, and then calculates the derivatives to high precision using the chain rule. It's a repeated application of the chain rule. And this is one of the more fantastic algorithms which has been developed in the last years. It is a little bit slower than using the analytical expression, but sometimes to implement an analytical expression can take a lot of time. And also in many cases, the functions you're developing are multidimensional functions, and it can be actually time consuming to calculate the higher order derivatives. We are mainly going to deal with first order derivatives and second order derivatives. So these quantities here would typically classify the system. Now then, what we would have next is what we might call the solver. So in project number 1, the things we need to implement are obviously a Markov chain Monte Carlo, chain MC. This is normally written as MC squared, Markov chain Monte Carlo. And in here, you will have a sampling rule. And the sampling rules which we are going to look at is the basic one is the Metropolis. But then a little bit later, we will also look at something which is called Gibbs sampling, which is actually a simpler variant of the Metropolis sampling. So the Metropolis sampling is something we are going to extend to what's called importance sampling, which is going to give us a better way to sample the space of possible moves. And this Metropolis sampling is then typically called Metropolis Hastings sampling or importance sampling. That's another name for it. But the Metropolis algorithm plays a central role here. So the Markov chain Monte Carlo approach is the basic mathematical algorithm, which we are going to look at. The Metropolis algorithm is just a way for you to accept a suggested move in a Markov chain or reject that suggested move. So think of the Markov chain Monte Carlo method as the basic mathematical method which you're going to implement. That defines the main algorithm. So the main algorithm follows from the Markov chain Monte Carlo theory. And then inside this, you are actually going to make moves. In our case, this is going to be coordinate space. We're going to move a series of random walkers in order to sample all possible configurations in space. And the way we sample these and accept or reject the moves is given by a sampling algorithm, which is then called the Metropolis algorithm, or the Gibbs algorithm if you want to implement that one. So there's going to be a sampling. So the Markov chain Monte Carlo is going to be the main method. Now, inside here, we are going to need some other things. And when we deal with a stochastic evaluation of an integral, one of the things we want to do is to evaluate the statistical errors. So one of the advantages which we have now is that we have a probability distribution given by the trial wave function, and then we want to evaluate errors. So this leads to another set of methods in the solver, which are called resampling techniques. So this is a statistical tool which is widely used. And for those of you who have taken let's say a course in machine learning or advanced statistics, you have encountered popular methods So I'm just setting them in as a sub-methods here. So one of the popular methods called the bootstrapping, which we are going to look at. There's a method called the jackknife method. But the method we will focus on is a method which is less used in machine learning, because we are going to produce millions of data. And this method is called the blocking method, which allows you to actually get a precise estimate of the error without having to calculate the covariance matrix. And that's something which allows us to save a lot of CPU cycles, because we just need to have one single loop. We don't need a double loop. So the covariance requires a double loop over all of observations. If you have a single loop and you have a 1 billion Monte Carlo cycles, it means that if you want to calculate the covariance with that, you would need to evaluate a double loop with 1 billion squared calculations, which is something you don't want to do. So resampling techniques play a very important role. So let's mark that one, resampling methods. So we want to evaluate errors. We need to develop the theory for Markov chain Monte Carlo methods. And from that, we are going to look at the Metropolis algorithms and the Gibbs algorithm for sampling. We are going to have to deal with the resampling methods to evaluate properly the errors. Now, another thing which we are going to need now is to find the optimal parameters. So all these ingredients are ingredients which we need to bake into our program. So the optimal parameters alpha are those parameters where the calculation of, if we now take the, let's rewrite this as a partial derivative because that's more correct, because we have many such parameters. So let's put an alpha I here, and where I goes from 1 to up to n, which are the total parameters which we have. So what we need to evaluate then are the derivatives of this local energy as a function of these parameters alpha with d alpha I. And since this is an optimization problem, we actually want these derivatives to be equal to 0. This is going to lead to a set of methods which we need also to implement. So remember now that we have a trial wave function. And in this, we don't know whether this trial wave function makes sense or not. And we are going to evaluate the integral which you see here. So let's mark it again. So we are going to evaluate this integral, and that is an integral which will depend on the parameters we are using to define the model. So we have a model for the trial wave function, and this model for the trial wave function depends on the parameters, and that means that we want to optimize it. And when we optimize it, we need a method to find the derivatives of the expectation value as a function of these parameters. Now, in order to find these derivatives and to use them in order to find the optimal parameters, we are going to need mathematical methods to optimize a function. And this leads normally to gradient methods and optimization problems. And the kind of gradient methods we are going to look at are things like the Newton-Raphson method. We are going to look at standard gradient descent. We are going to look at something which is called stochastic gradient descent. So those of you who have taken a course in machine learning, you have already encountered many of these methods. But we will dedicate a little bit more time to it because there are also other methods which can be efficiently implemented in these specific cases we are looking at. So gradient methods are going to play a very important role here. And this is a dedicated topic in a little bit later here, but we need to implement that. So what I'm doing now is just to list all the ingredients which we gradually are going to put into a variational Monte Carlo program. Now, when we have this now, we still are not yet done because we would obviously like to tune our program to high performance computing facilities so that we can run as fast as possible. So the next topic which we need to think of is how do we utilize high-performance computing facilities? High-performance computing. Performance computing. So this leads to topics like parallelization, and this is normally done with MPI, message passing interface, or OpenMP. We also can vectorize our program, which is extremely useful when we compile the program. So these are all techniques which we will cover when we are discussing how to optimize the program for efficient usage on high-performance computing facilities. So we can actually have our program to run faster, or rather, we are going to use more cores and CPUs in order to get more statistics in the same amount of time which we would have spent if we were just to run on a simple PC with just one core. So the high-performance computing aspect comes in now due to the fact that we are dealing with stochastic samplings of an integral. And if we now go back again to the equation which we are going to deal with for large fractions of the time in this course here, this equation here, when we do a stochastic evaluation of an integral, we simply want as many samples as possible. And that means that we are going to deal with CPU-intensive programs, and the more cycles, the happier we are. Because hopefully then, when we have more and more data which enter the evaluation of that integral, we are hopefully getting closer and closer to the exact solution. Now, remember now that the exact solution, when you have the trial wave function, is actually the value of that integral. In some cases, we know this value of the integral if we have an analytical trial wave function, which gives the exact solution, as we will have if we don't plug in interactions. However, in general, we don't know the answer to this integral. And that's why we simply just want to run with as many cycles as possible in order to get as good a statistics as possible. So this is one of the main motivations for why we deal with high-performance computing topics. So these are ingredients which we are going to bake in gradually in order to develop a professional variational Monte Carlo program. Now, at the end, when we are done, we can actually now, when we have this framework, we can actually reuse this one or parts of it if we want to include neural networks to solve the equations. So if you do that variant of project number 2, what you will need then is much of the same machinery, but the difference now is that the neural network is actually going to compute your wave function. So instead of you plugging in a mathematical expression for the wave function, which is based on your insights about the system, all the knowledge you have accumulated about quantum mechanical systems, now you're simply going to say, I don't care about this knowledge. I'm going to let a neural network find the best possible representation of the wave function. You can always guide the neural network. This is what leads to the possible version of project number 2, and then you will simply reuse everything you've developed here, but you will replace the wave function with a neural network. Alternatively, many of these ingredients can also be used in other many-body methods. And for those of you who perhaps are doing a thesis in quantum chemistry, Hartree-Fock methods, configuration interaction theory, copper cluster theory, and other methods may be more interesting as a variant of project 2. But the kind of things we are building up now, this kind of split between a system where you now can add functionality by looking at different types of Hamiltonian operators, different types of trial wave functions, and so on, and then have a solver class, for instance, that gives you much more flexibility in developing a program. So these kind of ingredients which you see here now, they are ingredients which we will have to bake in when we write a program. So what I wanted to do after the break now is actually to look at the mathematics of a simpler case, the harmonic oscillator, so that we can build that in to the program and develop functions like the function for the trial wave functions, the function for the local energy, and then try to implement things like the Metropolis algorithm. So after the break, we are going to look at some system cases here, some familiar one, the harmonic oscillator and perhaps the hydrogen atom. And then we are going to look into the theory of Markov chains. And in particular, we're going to derive the Metropolis algorithm. So some of you have already seen that. For those of you who have not seen it, this is something we will dedicate parts of this lecture and also the beginning of the lecture next week, so that you understand what defines the basic elements in the Metropolis algorithm, which is perhaps one of the top 10 algorithms in numerical mathematics. So I will pause the recording now. So welcome back, everybody. What I want to do now is to start looking at the basic ingredients which we need to have in project number 1. And we are going to look at now the plain harmonic oscillator. We are not going to look at an interaction between the particles. So that means that the total wave function is just going to be the product of single particle wave functions. And if we now go back a little bit to what we did, we are going to look at some specific types of trail wave functions. And in our case, we are going to pay attention to both the harmonic oscillator and perhaps other types of trial wave functions. But essentially, it's going to be the harmonic oscillator, which is going to keep us busy here. So one of the things which we can start with then is actually to look at our system in one dimension. And we are going to look at the system of one particle trapped in a harmonic oscillator. So let's now look at the type of problem which we have. So we are going to look at the one-dimensional, and it's very easy to extend this to 2 dimensions and 3 dimensions. So we have analytical expressions always for these different cases. But let's remind ourselves of the one-dimensional harmonic oscillator. So HO stands for our harmonic oscillator. And if we look at Schrodinger's equation for this specific case, plug that in, what we're going to have now is an equation where we have minus h squared. There is a kinetic energy operator, and that's given by the second derivative of the wave function. And now I'm simply going to set in the an expression for the wave function which does not depend on this trial wave function, because here we know the exact answer. So this is going to depend on x here. There's going to be a function psi of x, and then we have plus, and then we have the harmonic oscillator potential, which is typically given by 1/2 times the mass of the particle, and it contains the harmonic oscillator frequency, and it contains x squared, and then we have a psi of x, and equal to the energy times psi of x. And we know that the energy is discretized, so we would have an energy eigenvalue, which is given by h bar omega, and then we have this quantum number n plus 1/2. And n takes values from 0, 1, 2, and in principle up to infinity. So we have an infinite set of bound state for this system. Now, one of the things which we need to do first in order to prepare everything is to actually scale the equations. So this is something which is very important, because it's going to bring in a natural length scale, and it's going to give us an understanding on what kind of parameters we need when we are going to implement the plane or straightforward, or what many people call the brute force Metropolis algorithm, because then we are going to let the random walkers jump in space, and we are going to guide this by a step size. So you can let your random walker jump around with very small steps. Then you will sample a very small part of your configuration space. If you give a too large step size, it's going to jump with huge steps, and then you may actually move into regions where the wave function squared, your probability, is equal to 0. So when we're going to implement the plain Metropolis algorithm without any form for importance sampling, so importance sampling means that we are going to guide the jumping according to the probability distribution. So we're going to make a slightly more intelligent jumping. But in the standard implementation of the Metropolis algorithm, we're going to let our random walkers jump according to a specific step size. We are coming back to that. So scaling the equations is going to give us an insight about how we should jump in the space of possible positions. So guys, feel free to interrupt me in case what I'm saying now sounds unclear. But let's look at the scaling first. And many of you are familiar with this because this is a standard trick, which is also used when you want to rewrite the equations in order to find an analytical solution. So the first thing we're going to do now is to introduce dimensionless length. So the dimless length is now introduced by adding a parameter. And this parameter is not going to be the same as our parameter in the trial wave function, but we could say now that we have a dimless length. So this is a dimless length, which we call for rho. And this rho is given by a parameter gamma times x. So x has dimension length. That means that gamma must have dimension inverse length because we want to have rho to be dimensionless. So keep in mind then that the dimension of x is length. The dimension of gamma is length inverse. So that means obviously that x, and I hope you don't get offended if I put up this trivial relation, is rho divided by gamma. Now, when I then plug this in to Schrodinger's equation here, what I'm going to get now is minus h squared times gamma squared divided by 2m. And then we have the second derivative with respect to rho now. And this is going to contain the wave function. And remember now that the wave function, the argument to the wave function, has always to be dimensionless. So we've been scaling it now. So psi depends on rho now through this scaling. And then we have plus 1/2. And now we have this m. Now we have to be a little bit careful because we have to bring in this parameter, which we have. So we have a rho cubed, but now we need to divide this one by h bar squared and multiply it with this parameter gamma to the power of 4. This is multiplied with psi of rho, and this is equal to the energy times psi of rho here. Now, what I'm going to do next is simply to multiply away. So I multiply away with m divided by h bar divided by gamma squared on both sides of the equation. And then what I get then is now just a equation which has a minus 1/2 of d rho squared. So this means that what I have now is a, and remember now that the wave function doesn't have any dimension. So we have gotten rid of the dimensionalities here, but now we suddenly have a lot of constants in front of here. So we would have an m squared, omega squared, and then we have this rho squared, and then we have omega, psi. This is multiplied with psi of rho, and this is divided by h bar squared gamma to the power of 4. And the, sorry, I actually had I anticipated the result. No, sorry, it's not like that, like this. So this should actually be gamma to the power of, I think I had a wrong power here. This should actually be to the power of 2. Sorry for that. Okay, so by doing this, and this parameter here, I anticipated some results here. So this should actually be, this is the way it should look like. Okay, so what I do next now is simply to require, when I look at these parameters which I have here, since these are all parameters, I can now choose this gamma as I want. And I'm going to choose this gamma so that the equation which we have here, this m squared times omega squared of h squared of gamma to the power of 4 is equal to 1. This is going to introduce what we will call a natural length scale. So when I do that, what I get is that gamma squared is equal to h bar divided by m times the frequency here. And that means that what I have now is that gamma, which has dimension inverse length, and you can easily check that, is given by m divided by omega. So this brings in what we might call a natural length scale. Now, when we go back now to the harmonic oscillator, so if we now set typically omega equal to 1, h bar equal to 1, so when we choose natural units, then it's common to fix these parameters. So we would have h bar equal to m equal to 1. And obviously, if we pick then omega equal to 1, then we would have gamma equal to 1. So that would be a guess for the way the random walk is going to jump into space. So we will also have the speed of light. So these are so-called natural units. And you see now that your gamma is going to depend on the parameters of the harmonic oscillator potential. Now, let's now look at the form of the trial wave function. So for harmonic oscillator, the trial wave function is going to be given in one dimension. And we know that the exact answer is going to be given by this equation here, multiplied with some parameters, but for alpha squared equal to 1. That's where we're going to have the exact answer. Now, what we can do next now is to define the local energy. So this is what we would need to program. So the local energy then would simply be given by 1 divided this psi of t, and then we would have minus. And now we are just going to deal with this this scaled equation. So we're going to have a minus a half, and instead of rho, I'm just going to call this for x. So we are going to have a dx, and I'm assuming now that x is dimensionless. So I'm just replacing rho with x. I mean, these are just variables, so we can name them whatever we want. And this is going to be given by 1/2 plus x squared. So this is going to be the harmonic oscillator potential we're going to program. And we will always use these kind of units in the calculations here. And then this is multiplied with psi of t. Now, to calculate the derivative is actually pretty easy. And when we do the calculations then, what we get is that this is equal to 1/2 of alpha squared plus x squared. And this is one of the things you actually are going to need to implement in your code. So the alpha to the power of 4 comes from the second derivative of the wave function. So I'm just giving you the answer here. So this is the local energy. Then, when we want to calculate the expectation value of the energy, we're calculating this expectation value here. So this is going to be an integral over d of x from minus infinity to plus infinity. I'm going to have the quantum mechanical trial wave function, which defines the probability distribution. So I will now have a p of t of x as a function of alpha, and multiplied with this local energy, which depends on x and alpha. So when I look at the integral here, this is going to be given by minus psi squared, and then I'm going to have the wave function squared. So I will have e to the minus alpha squared times x squared. And this is now multiplied with the local energy, which is a half of alpha squared plus x squared, or 1 minus alpha to the power of 4. And this is divided by the wave function squared. So I would have a minus. And since I have the wave function times the wave function, I get rid of the factor of a half. So I have d of x of e to the minus alpha squared times x squared. Now, this integral gives us now, as a result, it gives a very nice and simple answer. And when I plug in the formula for the e to the minus x squared, I just look up a numerical table over that, then we will find that this is given by 1 over 4 of alpha squared plus 1 over alpha squared. So this is the expression for the energy. And we are going to find the optimal value, alpha. So in order to find the optimal, then we need to take the derivative of the expectation value. And we need the derivative to be equal to 0. So that's where we're going to find the minimum. And if we take the derivative of that function there, what we find then is obviously that this is equal to 1 over 2 times alpha minus 1 over 2 times alpha cubed equal to 0. And that leads to alpha equal to 1 at the minimum. And if I plug in alpha equal to 1 into this expression here, what we are then going to get is that the energy, in this specific case, EL of alpha equal to 1 is equal to 1/2 here. So I'm just going back to the expression which you see here now, this expression, and I'm going to plug in alpha equal to 1, and then I simply end up with the answer, which simply says that in these dimensionless units, then alpha is, the energy is equal to 1/2. So remember now that what we have done here, in this specific case, we've actually put h bar equal to c equal to the mass of the particle. So we are using these specific natural units. And also, one of the things which we've done here, we have absorbed the value of the oscillator frequency. So remember now that when alpha is equal to 1, this alpha equal to 1 is going to play the same role as what we did up here. It's going to play the same role as this parameter gamma. So this corresponds to us having a natural length scale with a frequency which is equal to 1 for this specific problem here. So this is the one of the first tests we need to do. So this corresponds to omega equal to 1. If I have another value of omega, I will find another minimum. So we have to be a little bit careful with the value of omega. So this will also define, for this alpha equal to 1, it's going to define a natural step length when we are jumping in randomly in the space of the positions. So this is one step. Now, there's another important ingredient. So normally, we don't know the exact wave function. Normally, we don't know psi of t, or rather the exact wave function. So let's just put exact on that one. And then the question is, how can we judge? Can we judge from this trial wave function, judge from psi of t as a function of these parameters alpha? In this specific case, we're just looking at the first step with the one particle in one dimension. How can we judge from psi of t whether we are close to the exact function, we are close or equal to the exact wave function? So there is actually a measure which we can use in order to find whether we have the exact wave function or not. So when we calculate the energy with this trial wave function, we just get a number. We don't know whether that number is close to the exact energy for that specific integral we are evaluating or not. So the question is, do we have some quantities which we can evaluate in order to see whether we have the exact energy or not? So as a question to you guys, I mean, feel free to unmute yourself. If I have the exact wave function, do you know of some quantities which give a result which is very simple and which we can use to say that now we are having the exact wave function? There is an important statistical quantity. So this is a kind of hint which I'm giving you. So any good suggestions? Feel free to suggest in the chat or unmute yourself if you want to.
We could check the variance of our results.
Fantastic.
Because if it's the exact, it should be 0.
Exactly. So this is one of the quantities which is very much used in Monte Carlo calculations. The only problem is that people, when they are varying the parameters, so you could actually vary the variance or vary the parameters so that the variance is equal to 0. So let me define the variance first, mathematically, because this becomes a quantity which we are also going to calculate here when we're going to estimate the errors. So the variance formally is defined as follows. So if we take a probability distribution, we are going to write this as a sigma squared. This is, if we now look at the variable x, this is going to be defined as the integral for x squared multiplied with the probability distribution for x. And x is defined in some domain, which we haven't specified, minus the expected value of this variable x. So that means that what we would have then is an x multiplied, this is the definition of the expectation value. So we're going to square that one. So this is the same as the expected value, the mean value of this variable x. So it's given by the first moment. So here we have a probability distribution. And this is the formal definition of the variance. Now, if we are looking at a quantum mechanical object, if we want to calculate the quantum mechanical variance, what we actually need to do then, and now we can look at the expected value of the Hamiltonian here. If we take that one, this is now given by the following quantity. In our case, when we do it quantum mechanically, so we would have an integral here, and now I'm just writing the true wave function without any parameters. I would have the quantum mechanical operator squared multiplied with psi of x of d of x. I'm just thinking of this as a one-dimensional problem, just to simplify the notation a little bit. And this would now contain psi squared here. Now, if I have psi times psi of x, h times psi of x, if this psi of x is an eigenstate of the problem, this is simply given by the eigenvalue times the eigenfunction. This means that if I have the exact wave function, if this psi t is equal to the psi exact, so this is now the exact solution. It could be one of the infinitely many states of the system. If this is the case, then you see now that this quantity here, which we evaluated, h squared, becomes simply equal to this quantity epsilon squared, and then this is multiplied with psi squared, because we just have a constant of d of x, and then we divide this by the norm again. And now I'm a little bit sloppy here, and I'm dropping the integration domain. So what we end up with then is simply epsilon squared. Now, if I then take the same quantity here, which would be the expectation value of the system squared, this is also equal to epsilon squared. So the variance of this Hamiltonian here will then be equal to the expected value. So I'm now setting up the quantum mechanical definitions of the variance, the quantum mechanical variance. So that will be given by now a E, the mean value. And we see now that this is equal to 0 if psi t is equal to the exact value. Now, to calculate the variance is something which is a little bit more tricky. And I'm just going to give you the answer here for this specific case. So if we now go back to psi of t as a function of x and alpha equal to this trial wave function, which we opted for here, alpha squared times x squared. Now this has been, again, put back into a dimensionless variable. So x is a dimensionless quantity here. Now, if I now look at the variance for this specific system, so this psi for the energy, and now I'm going to write this as a function of alpha, you can get an analytic expression here, which is simply given by, and I'm just going to list the expression of 1 plus 1 minus alpha squared. And this is divided by 3 times 4 times alpha squared minus the expected value of the energy squared. And in our case, we know the value here. So in case we now have the exact answer, what you would see then, if we plug in the exact answer, we can now simply plug in alpha equal to 1. We know that the energy for the exact, or what we know is the optimum value for this specific wave function is given by 1/2. And if we then go back and plug that in, so you can see now if I plug in alpha is equal to 1, the first term here becomes just equal to 1/4. So this quantity is then equal to 1/4. And then I'm subtracting the exact or the value for the energy at the optimum parameter alpha. So this will simply be 1/2 squared. And we see that that one is exactly equal to 0. So this is something which we can use as a kind of guideline. If I were to give you different types of wave functions, and having different types of wave functions, you can then say, okay, which one should I pick? You would obviously pick the one which gives a lower energy. That would be your first reaction. And then normally what you will see is that the one which has the lowest energy is also the one which has the smallest variance. And then you will say that, okay, this function, this trial wave function, which I've been using, has a small variance. I know that the variance ideally should be equal to 0. And then what I would do then is simply to now say that, okay, with this variance, if it's getting closer and closer to 0, I would prefer a trial wave function which gives me a variance which is as close to 0 as possible. So this is the kind of way you would now proceed in testing your trial wave function. So these are important ingredients in the tests and the checks which you need to do in order to develop a variational Monte Carlo program. Any questions so far? So there's another small thing which I wanted to say something about. And you may now ask, how should I define this trial wave function? Can I be guided by something? Are there some features of the system which I'm studying which could reveal some important properties of the trial wave function which I could use in a Monte Carlo calculation? So remember now that the whole machinery which we are developing relies on you plugging in a trial wave function. When you have the trial wave function, which depends on some parameters, then what you end up doing is to evaluate stochastically an integral. And when you're evaluating this integral stochastically, you want to perform as many sampling as possible. so that you have a good statistical representation of the variables you want to define. However, sometimes you may not know what kind of trial wave function to pick. So for the harmonic oscillator, we are in a lucky situation because we know the analytical solution of a non-interacting system. And we know that that analytical solution should behave something like this, multiplied by a constant. And we can actually show now by setting it into the analytical expressions for the integrals, what we should get when we now have the optimal parameter alpha. And then we're actually getting the exact value. Now, the question is now, how can we define some minimal requirements for the wave function? So there are ways we can proceed. How to find psi of t. The project 2 variant with neural networks is actually a variant where you're letting the neural network find as much as possible of information for the trial wave function. But you could actually use some physics insights which are based on your Hamiltonian system. So let's look at a classic system which you have met many times. So let's look at the hydrogen atom. That's another of these cases where you have an analytical solution. However, the way we set up the analytical solution is something which is going to give us some insights about how to solve the equations. Also, when you scale these equations, you're going to get a natural length scale, which is going to be given by the Bohr radius. You may remember this quantity when you did the theoretical manipulations in order to find the analytical solution. So let's look at the Schroding equation for this system. So the Schroding equation for this system, if you look at the hydrogen atom, is just 1 h bar omega divided by 2m. We have the second derivative here, minus, and then we have some charge. We are going to put the charge equal to 1. And in this specific case, we have a constant here, which has, for atomic physics, is equal to 1.44 electron volts times nanometers. That's a typical value for that constant. There's the charge here, and then you have a distance r, which is the distance from the electron to the atomic nucleus. I put the charge equal to 1 here, and this is given by a psi as a function of r here. And this is our eigenvalue multiplied with this eigenfunction. Now, it's pretty common when you solve this problem here, you cannot solve it in Cartesian coordinates, but you would typically translate this one into spherical coordinates. And where r now takes values between 0 and infinity. Now, we know the exact solution here, and that can be written out. So you can separate the equations, and you can then write this out in terms of free coupled differential equations. And the one which gives you the energy is the one for the radius r. So the essential differential equation, which is going to reveal some important properties. So this is a differential equation for r. That differential equation is given by when we now transfer everything to spherical coordinates. So this is going now to be rewritten in terms of d of r, d dr. And now you're going to have an additional parameter which comes from the fact that the orbital momentum is discretized. And we are just going to look at an orbital momentum now, which contains an orbital momentum equal to 0. And this goes up minus, and then we have k times the charge divided by r. And this is multiplied with the radial wave function. And this is given by the radial eigenvalue of r as a function of little r. And then we are going to put in L equal to 0. We're going to use these natural units. We're going to put h bar equal to the charge, equal to the speed of light, equal to the mass. So everything is just put equal to 1. And these are normally called natural units. Then we can scale the equations here. And when we now rewrite it, what we get then is a differential equation, which now is going to depend on this quantity R. So let's now look at the equation now when we have gotten rid of all these constants. We have just put them equal to 1. So if I now look at the local energy here as a function of R, this is now going to be given by, if we use the definition of the local energy, it's 1 over R. And now I write out the derivatives. So I'm going to get a second derivative with respect to R squared. There's going to be a minus. There's going to be a factor of 2 over R over d dr minus 1 over R. And this is all multiplied with R times R, R as a function of R. Now, when we deal with quantum mechanical systems now, what we see here is that R, when R goes to 0, we are running into problems. When R goes to 0, we have a divergence in this 2 divided by R d dr, and this term which goes like minus 1 over R. There are some important assumptions here. And these important assumptions are the following. So when I take lim of R goes to 0 of the derivative of the wave function as a function of R, of d of R of n, this is assumed to be a constant. If not, we would get kinetic energies which would diverge. So we cannot actually deal with that. So it means that the term which we have with the second derivative is something which is going to approach a constant. It means also that the term which we have here is something which is going to approach a constant. So these are requirements which we actually put on the wave functions in order to find the solution. I don't know if you discussed that when you took a basic course in quantum mechanics. But these are important requirements in order to find a solution to Schrodinger's equation. And that leads to the set of L squared integrable functions. So that's in mathematics. This is a huge, subdiscipline in mathematics. It's a huge field in mathematics to study the properties of these kind of differential equations. Now, for us, what it means is that we can approximate this local energy with the following. So when we now take the lim over R goes to 0 of this local energy as a function of R, what we are interested in now are the terms which are going to survive. And these are the terms which lead to the divergences. So we take away the first term, which is the second derivative, which just approaches a constant, and this constant is not of any interest. So we're going to get a d of R minus this term 1 over R multiplied with R. And now what we want is actually to cancel these divergences. So we want this one to actually just be equal to 0. So we have a divergence in the kinetic energy and a divergence in the potential energy, which we want to cancel when R goes to 0. So that means that I have a differential equation now, and I'm assuming that R is not necessarily 0. So what we would get then is a differential equation which runs like d of R times R. And now I'm just putting in the R here. And that means that what I get is now a differential equation which looks like this. So I would have an R here, and then minus, and then I simply have 1 over R here. And then I multiply away R, and that leads to a differential equation which runs like d of R dr equal to minus 1 divided by 2 times R. I could put in a charge here if I wanted to. I don't need to put the charge equal to 1. So you could actually put in the charge of the specific atom. And what you get then is a solution where R of R is equal to E. In order to cancel the divergency, you need a solution now which goes like 1 over half times R. So that's the solution to the problem. And this tells you why the hydrogen solution, which you have seen before, must have this exponential term. That exponential term ensures that you cancel a divergency. So that means that now you could define a trial wave function, so Ct of R, as a function of alpha, which is equal to E minus some parameter alpha multiplied with R. If you have a repulsive potential, this is in case of an attractive potential, if you have a repulsive potential, then what you would get then would be a exponential which has, instead of minus, it has a plus. So this is the way you would typically attempt to find a minimal constraint on your trial wave function. This is something which we are going to use a little bit later when we are bringing in the interaction between the particles which are trapped in a harmonic oscillator trap. So when we are not looking at any interactions between the particles, we are now simply going to use the harmonic oscillator as a trial wave function. So the first step in our coding here is now to try, since we are dealing with a harmonic oscillator problem, is simply to try out to implement this specific function here. In this specific case, we have a very nice expression for the trial or the local energy. We know that the local energy here is given by this function here. This is something which we can integrate analytically, and we get a closed form expression in terms of the parameter alpha. With that parameter there, we have an expression for the optimal parameter, which gives alpha equal to 1, and that gives us an energy which corresponds to what we would expect from the analytical result when we put the different units, different constants, h bar, speed of light, the mass of the particles equal to 1. And this is something which allows us to have a good benchmark of the calculations here. So I wanted now to simply bring back again the Monte Carlo code which we have in the Jupyter notebooks, and this is where I'm going to end the lecture today. So let's just take a quick look at the Jupyter notebook here. And so this is the notebook which you can fetch from the website of the course here. And this should actually be, yeah, no, not this one. It should be this one. Here we are. So this notebook here implements this harmonic oscillator step. And let's take a quick look at it here. So many of the things which we discussed are actually repeated in the slides here. So you can look them up again and repeat the calculation. So what I did here, let me just rerun this one. So coming back to the sketch which we had before the break, I'm now setting in or defining a function for the wave function. So this is now my harmonic oscillator as we defined in the lecture. E to the minus 1/2 times alpha squared times R squared. So it receives as argument R and alpha. And then I'm plugging in the analytical expression for the local energy. Later on, you may find it convenient to just calculate the second derivative numerically. And we are coming back to issues related to that. But for the harmonic oscillator here, we have an analytical expression. Remember now that if you want to calculate it numerically, that introduces new errors or approximations in the calculations of derivatives. So here we actually have the analytical expression. So this will be one of the things which you need to set in when you have done the paper and pencil exercises. And what I'm doing here is something which we will discuss in even more detail next week. So I'm running now a calculation of 100,000 Monte Carlo cycles. I'm defining a step size. This is how I'm letting my random walker jump in space. So you could think of this as 100,000 random walkers, or just as 100,000 steps I'm making in my integration of my approximation to the integral. I'm setting the old position and the new position. I'm just setting up an array here. And then I'm running over these variational parameters. So this is my outer loop. And here I know that the optimal parameters is equal to 1, but so I'm letting it run over a range of parameters. And then I just increase it by small steps. I define the energy and the energy squared. These are quantities I want to calculate. And now you see that I'm letting my random walker to jump in position space here. So it picks random numbers between 0 and 1. And that's why I have this -0.5 here, so that it actually produces random numbers between -0.5 and +0.5. And I'm having a step size here, which allows me to jump in space. So next week, when we are going to define the algorithm for making this sampling and derive it, the Metropolis algorithm, we are going to see then how we can actually calculate the next step and accept it. This is based on a ratio between probabilities. So I'm taking the wave function squared in the new position and divide that with the old position squared. This is what you see here. I define a new position, which is simply the old one plus the step size. This is my straightforward or brute force Monte Carlo sampling. And this is going to jump around in one-dimensional space according to the step size. Next week, we're going to discuss these things in more detail, but I just wanted to give you the kind of bird's view on what you will end up implementing. So what you see here is now my Markov chain Monte Carlo implementation with a Metropolis test in order to accept the new position or reject it. So if this random number is smaller than a given number, then I accept it. And then I set the old one equal to the new. I calculate my new contribution to the energy. I update the expectation value of the energy and the expectation value of the energy squared. And then I divide by the total number of cycles, calculate the variance and the expectation value of the energy, and then make the plot. So if I run this one, and this is where we're going to start. So I have 20 parameters. I define the energies. I also have exact energies. So these are the values which we plugged in during the lecture here. So I'm just plugging in these quantities in order to compare my numerical results with the analytical results. And this will be the first thing we want you to do. So try to do it as simple as possible. And then we can start adding complications. So next week, we are going to derive the Metropolis algorithm. And then we are going to look at how we can make more, better ways to jump in this coordinate space. So if I look at the energy, you see now I have a minimum at 1, as expected from our theoretical analysis. And this happens at, it gives a values of 0.5. And you also see that the variance is exactly equal to 0. And when you plot these results, you can then compare them with the exact values. So you have your computed energies, and we are going to discuss why these are a little bit more different from the exact one when we are far away from the minimum. But you see now that when you get to the minimum here, where the parameter alpha is equal to 1, you have the exact answer. So this is the analytical result. This is the numerical result. This is the variance, the numerical variance, and this is the exact variance. And you see that these are exactly equal to 0. So this is actually the kind of test we want you to start to develop. And this week, we wanted to go through more the mathematical details of the wave function. And then when we've done with that, we are now going next week to derive the Monte Carlo Markov chain machinery with the Metropolis algorithm. And then we're also going to look at something which is called importance sampling, which is now going to bring us a step further to a more intelligent jumping around in this space of random variables in order to sample correctly the integral. So this is where we're going to stop today. And these are some of the first steps we want you to do. You can use this Python code here as a kind of inspiration when you want to develop your own C++ program. Or if you feel more comfortable with Python first, you could actually use this one to start making your own program, or simply just run this one, and then get a little bit acquainted with what things mean. And next week, then, we are going to look at the Markov chain Monte Carlo machinery with the Metropolis algorithm, the modified Metropolis algorithm, which is the Metropolis Hastings algorithm. And we are going to see how we can implement these quantities numerically. So I hope this gives you a kind of bird's view, and that it's a little bit easier now to see the wood for the trees.